A buck regulator is a DC-DC converter which converts a higher voltage potential to a lower voltage potential. It uses a switching element to ensure steady DC output of required voltage. I am Reshma, and today we will discuss the operation of a buck regulator. In this video today, we will see how we can use the equations of previous videos to arrive at a starting point for designing a buck regulator. We will discuss on our following topics: inductor, average and peak currents of an inductor, losses of an inductor, switch and diode. Let us try to design a buck regulator in continuous conduction mode. Let the required output be 5 volt and maximum load current be 1 amps. Let the input vary from 8 volt to 30 volt. Let the inductor ripple current maximum be 30% of the load. Let it switch at 100 kHz. It is to be noted that we are dealing with continuous conduction mode of operation. Since the values are theoretical, they give us the starting point. However, they need to be validated in actual hardware. Based on these actual hardware measurements, some changes may be required in the design. We know that time is inverse of frequency. Hence, total time period is given as 1 by switching frequency, that is equal to 10 microseconds. Now, the ripple current is 30% of load current. Hence, Di is equal to 1 into 30%, that is equal to 0.3 amps. Let us calculate the value of the inductor when input is maximum, that is when input is 30 volt. We know the buck regulator output transfer function. Using this, we can find the minimum value of duty cycle which occurs at maximum input voltage. On substituting the values, the duty cycle amounts to 0.166. Now, we know that when the switch is turned on, inductor current is given as shown here. We know that the inductor ripple current is 0.3 amps. On substituting these values, we get the value of L. L is equal to 138 microhenry. Let us now calculate the value of inductor when input is minimum, that is when the input is equal to 8 volt. We know the buck regulator output transfer function. Using this, we can find maximum value of duty cycle which occurs at minimum input voltage. On substituting these values, duty cycle amounts to 0.625. Similar to our previous exercise, we can find the value of the inductor using the duty cycle considering the switch is turned on. On substituting these values, we get the inductor value to be equal to 62.5 microhenry. We can notice here that we have two values of the inductor. Which one should we be using for design? We have to choose the inductor with higher value. This is because if we use an inductor with smaller value, then at high line input voltage, we will have a ripple current more than 30% in the inductor. Thus, L is equal to 138 microhenry. Now, output load is 1 amps. We know that inductor average current is equal to load current. Hence, inductor average current is equal to 1 amps. From our previous video, we saw that inductor peak current is given as shown here. On substituting these values, we get 1 amps plus 0.18 into 1 minus t as inductor peak current. As we have two duty cycles, one with low input voltage and one with high input voltage, let us calculate peak inductor current for those two values. So, at 8 volt input, duty cycle is 0.625. With this value, we get 1.067 amps as peak. At 30 volt input, the duty cycle is 0.166. With this value, we get 1.15 amps as peak. We need to take higher peak current value while selecting an inductor. As we have seen earlier in our previous videos, the DC loss of an inductor is given as R inductor DC into I1 square plus I2 square plus I1 I2 divided by 3. It is also equal to R inductor DC into inductor average current square plus ripple current square divided by 12. On substituting the known values, we get this equation. Power inductor DC is given as R inductor DC into 1.0075. Here, we do not know the value of R inductor DC. This can be found from the inductor data sheet or it can be measured using suitable instrument. Let us now look at switch design. The switch voltage is given as input voltage plus diode voltage. We need to consider maximum input voltage. With this, we get switch voltage as 30.7 volt. However, in practice, the switch must be rated at least 30% more than this voltage. This will be around 40 volt. Let us now look at the switch current. Switch average current is given as D into inductor average current. Let us consider maximum duty cycle which occurs at minimum input voltage. This is when we have maximum switch current. Let us substitute these values in the switch average current equation. We get 0.625 amps. In practice, switch current must be rated at least 30% more than this value, which is around 800 milliamps. Let us now look at the conduction loss of the switch. We have seen in our previous videos that average switch power loss is given as shown here. Here we consider maximum duty cycle. We know that all values except RDS on. On substituting them, we get 0.629 into RDS on. The RDS on must be identified from the MOSFET datasheet. From our previous videos, we have seen that current I1 and I2 is represented in terms of average inductor and ripple currents. Let us substitute the value to get I1 as 0.85 amps. I2 is equal to 1.15 amps. We have seen earlier that switch loss is given as Vn into I1Tf plus I2Tr divided by 3T. From the above equation, we can see maximum loss happens when input voltage is maximum. We can substitute these values in this equation. The rise time and fall time can be found from the switch datasheet or it can be measured on actual hardware. Let us now design the diode. We know that diode voltage is equal to the input voltage when switch is turned on. Hence, we need to consider maximum input voltage. Therefore, diode voltage is 30 volt. However, in practice, diode must be rated at least 30% more than this voltage. This will be around 40 volt. The average diode current is given as 1 minus D into inductor average current. We have to consider minimum duty cycle which occurs at maximum input voltage. This is when we have maximum diode current. Let us substitute these values in the diode average current equation. We get 0.834 amps. In practice, diode current must be rated at least 30% more than this value, which is around 1 amps. Let us now look at the conduction loss of the diode. The conduction loss is given as shown in the equation here. We consider minimum duty cycle which occurs at maximum input voltage. This is when we have maximum diode current. Let us substitute these values in diode power loss equation to get 0.583 watts. In conclusion, we can say that the values calculated are for continuous conduction mode of operation. All values need to be validated in actual hardware. Some changes in values may be required based on actual measurements in hardware. All loss calculations need to be validated in actual hardware. In this video, we saw an example to design a buck regulator in continuous mode. We will learn more in our subsequent videos. Until then, let's keep exploring and learning. Thank you.